同学们、老师们、朋友们，大家好，欢迎大家来到旭月谈的技科篇。今天是22年的10月11号，星期二。按照上礼拜的内容，我们继续探讨非子上微测技术和生物电研究它们之间的这个联系我们过去呢这一天呢上一次吧，通过这个研究心电图的这个历史我们来进一步的了解这个生物电和非子上微测技术之间的关系。我们知道生物电它的本质实际上就是离子带电的离子或者分子它的一个运输导致了电势的不同因此引起这种放电也好带电的这种现象因此这个离子学说具有很强的这个主导的这个位置而非子上微测技术呢自然在这方面呢具有很强的这个应用的前景。我们过去几次呢我们通过了解这个从振荡电极测量电场到非子上微测技术呢测量离子的这个矿脉运输比如说世界上最小的单细胞到暗纹的幼虫的组织的周边的这种电流的测量大小和方向都可以通过非子上微测技术进行检测。这是咱们国家的学者呢对这个老鼠正常的大鼠进行电刺激以后将钙离子的运动和这种电刺激给它联系了起来就是说我国的科研人员已经开始把注意力呢放到了这种生物电和离子运输相互之间关系的这个研究上。那么为了更加深刻的理解这个生物电我认为从咱们这个心电图可能是一个切入口，而这个切入口至少它可以让我们从一个不规则的一种生物电的变化和直接关系到人体人类最重要的器官之一心脏它的健康状况做一个联系至少呢通过前人的这些个工作呢看看能不能给我们一些启发那么通过这篇综述呢从1842年的开始记录生物电到24年这艾因托芬获得这个诺贝尔奖，因为他设计了这个心电图机到1954年的开始这个标准化的心电图仪诞生经历了100年左右的这种奋斗和努力所以任何事情任何这个生命科学的现象如果我们真正透彻的理解它乃至把它应用到生产实践或者人类的生命健康这个过程都不是一件轻而易举的这个事情要经过甚至几代人的艰苦的这个努力。那么今天呢我们将就这个心电图咱们其实所有人都比较熟悉的比如几个风几个波我很荣幸呢这个在这个通过搜索引擎呢找到了一个美国应该是护士协会吧护士学院学会的这么一个教科片我认为他介绍的还是挺全的给我的启发也不小我也提醒大家呢注意这个片子里的这个两个部分吧，一个是涉及到有关离子部分，还一个呢自然就是这个他们是如何产生电压的，或者说他们是和这个电压差之间有什么关系至少这个呢是我个人认为咱们应该注意的这个重点好下面呢就请大家呢观看这个片子，这个片子还不短所以呢大家可以耐心的把它看完。好，那么咱们下次呢我想找一些个咱们非常微测技术 所获取的一些个这些个电信号，然后我们也可以尝试着分析分析它这些个起伏各自代表什么，是吧？至少我们可以在这个方向上去集中大家的智慧呢，咱们一起思考思考。好，那么下次见。
Let's look at a single heartbeat on EKG. So here on the right side, we have a single beat on EKG, and we're looking at lead 2. Lead 2 has a negative electrode on the right hand and a positive electrode on the left foot. In a healthy heart, the wave of depolarization overall runs from the top right to the bottom left. So you can see that lead 2 measures voltage created in this direction. Therefore, lead 2 is commonly singled out for more simple information, such as heart rate and rhythm, because it gives you a pretty good view of the waves, particularly the P wave. Often people say that lead 2 is the best lead to see the P wave. An EKG gives us information on voltage over time, or the change in voltage over time. So voltage is on the y-axis, time is on the x-axis. Every small box running in the x-axis or time direction represents 0.04 seconds. And there are 1, 2, 3, 4, 5 small boxes per every big box. So you can do the math and you can calculate that each big box represents 0.2 seconds. Conduction starts at the heart's dominant pacemaker, the SA node. The SA node initiates waves of depolarization that run through the atria and go to the AV node. And on EKG, this depolarization through the atria is seen as this purple wave here called the P wave. The P wave is usually about 2 small boxes or 0.08 seconds. And again, the P wave represents atrial depolarization. And what happens after the atria depolarize? Well, you get subsequent contraction. After the signal reaches the AV node, conduction slows down. And this is for a couple reasons. One is that AV nodal cells are smaller in diameter than the other cells. And as a rule, the smaller the diameter of the cell, the slower the conduction. In fact, AV nodal cells are among the smallest diameter cells in the body. Also, conduction runs primarily through calcium channels in the AV node. Calcium channels have inherently slow kinetics, and this is in contrast to fast sodium channels that we see in the ventricular conduction system. This delay in conduction is really important because it allows time for the atria to contract and relax, which optimizes the time for the ventricles to fill. So again, we have the signal leaving the SA node going to the AV node where conduction slows down. This all happens before ventricular depolarization. On the EKG, the time it takes from the beginning of atrial depolarization all the way up until ventricular depolarization is seen as the PR interval. And the PR interval is typically 0.12 seconds, or 3 boxes. It shouldn't ever be longer than 0.2 seconds, or something's wrong. The signal travels from the AV node to the His bundle. And once we hit the His bundle, this is where conduction starts moving rather quickly. The His bundle bifurcates into the left and right bundle branches. And these branches branch into terminal Purkinje fibers. The depolarization from the His bundle down the bundle branches and to the Purkinje fibers leads to mass depolarization of ventricular cells and is seen as the QRS complex on EKG. Again, the QRS complex represents ventricular depolarization. And like we said before, this is very rapid because we're using fast-acting sodium channels now. So typically, the QRS complex is about 0.12 seconds. It shouldn't be any longer than that. Early on depolarization, the septum's depolarizing, and the septum depolarizes from the left septum to the right septum. So you have the wave of depolarization going from the left septum to the right septum. You'll notice that this wave of depolarization moves in a different direction than lead 2, which is why you get this first initial negative deflecting Q wave on EKG. However, quickly after, the wave depolarization spreads throughout the ventricles, which is why you have the positive, high amplitude R wave shortly after. Something else to note is that during ventricular depolarization, you also have atrial repolarization. So at the same time as the ventricles are depolarizing, the atria are repolarizing. However, the EKG signal that you would see from atrial repolarization is actually lost because the QRS complex dominates, since there are far more ventricular cells than there are atrial cells. So you don't see the atrial repolarization on EKG because it's buried in the QRS complex. So just after ventricular depolarization and in the initial phase of ventricular repolarization, there's a flat segment on the EKG known as the ST segment. And the ST segment represents a period where there's no net current. That's to say there's no large electrical vectors in any direction. However, this doesn't mean there's not a lot going on. During the ST segment is when the ventricles are contracting and are pumping blood to the aorta and to the pulmonary artery. Finally, the ventricular cells repolarize, and this is seen as the T wave on EKG. The T wave is flatter and longer than the QRS complex because repolarization is a slower process than depolarization. And again, this represents ventricular repolarization. The T wave typically takes up about 4 boxes, or 0.16 seconds. Now, something you might be asking yourself is, why is the PR interval called the PR interval when it goes from the P to the Q wave? Well, remember we said that the PR interval is from the beginning of atrial depolarization up until the start of ventricular depolarization. Sometimes there's no Q wave on the EKG. It's just not found. So ventricular depolarization, or the start of it, is actually the start of the R wave, which is why it's called the PR interval. If there is a Q wave, you can call it the PQ interval. However, to generalize, we call it the PR interval for the times that the Q wave is lost. Something else you might be wondering is, why is the T wave positive as well as the R wave? Why are the waves representing ventricular depolarization and ventricular repolarization in the same direction? And to answer this, you need to remember 2 things. One is that the EKG gives you information on the difference in charge. So it gives you information on the changing imbalance of potential. The other thing to note is that the epicardial cells repolarize before the endocardial cells. What do we mean by that? Well, remember how we said that the wave of depolarization goes down the bundle of His, the right and left bundle branches, to the Purkinje fibers. So you can imagine that the cells on the inside, or the endocardium, depolarize first, and the wave of depolarization spreads to the outside because we have the Purkinje fibers spreading the depolarization to the outer cells, or the cells of the epicardium. Let's cut out this part of the heart so I can show you in more detail. So remember, the EKG sees cells at rest as being positive on the outside. The wave of depolarization comes down and depolarizes the cells in the endocardium first. So those will be seen as negative, while they're still positive on the outside because the depolarization hasn't gone through yet. Eventually, the endocardium and the epicardium will be depolarized. And while typically cells that depolarize first repolarize first, it's different in the heart ventricles. Epicardial cells actually repolarize before endocardial cells. So the EKG sees them as positive before endocardial cells are positive. You'll notice that during depolarization, the vector created, and during repolarization, the vector created, are both in the same direction, which is why the peak of the QRS complex and the T wave are in the same direction.